Okay, so why don't we start with a really classic example of a kind of question that you might be asked. This isn't anything new, I'm just starting with a review example. But I think it kind of summarizes all the things we just talked about in the last, 5 minutes. Say you've got a running back, football example. He's moving at 7 meters per second, and he's going to get tackled by a linebacker. This is just such a classic collision, right? The question is, what's going to happen to them after they hit each other? Let's draw a bit of a picture here. Do you guys know what the 250 degrees means? Which way does 250 degrees imply? If I were to draw like a coordinate grid, the standard way mathematically is that this axis is 0. So that means that 250 is like, if this is 270, if that's 90, if this is 180. If someone's traveling at 250 degrees, they're traveling more or less this direction right here. That make sense? So there's a running back traveling that way. Then there's also a linebacker. I'm going to draw it over here for now, but I'm going to move this in a second. The linebacker's traveling at 10 degrees. So 10 degrees would look something like this. Again, this would be 90. This would be 180. This would be 270. This would be 0 degrees. They're going to collide with each other. If you understand your vector concepts, we need to make it maybe first so that all of these things are going to crash into each other. Let's see if I can get that other one in there too. Not the 180. There you go. So I'm going to take all of these. I'll put them right about there. Take this one right here. Let's move this one down there. There we go. No, come on. There. Does that kind of make sense how the picture is going to work? Right. They're going to crash into each other. Here's the point of intersection. And the question now asks, what's going to happen? Who's going to win this collision? Is the running back going to win the collision? Is the linebacker going to win the collision? Maybe more importantly than that, like which way are they going to travel? Because I want to know the velocity of the combined impact. In general, who's coming with more momentum? The running back or the linebacker? Is it clear why it's the linebacker? The running back has a lower mass and a lower speed, right? The linebacker has a higher mass and a higher speed, but we also got to account for the angles. So hopefully this is something that you're somewhat familiar with. We need to break this up into vector components. Okay. I like to draw maybe it's something like this. I'm going to draw in green right here. This guy that was traveling, like say downhill, he has a bit of momentum that's going in the y direction. And I'll use a lot of colors to help coordinate this. But he's also moving a little bit in the x direction. See how that works there? There's some component of it going down, some going over. And then to kind of keep the color coordination working, this guy right here is traveling somewhat in the x direction. But he's traveling uphill in the y direction. Like that. Okay, we need to break this up into its vector components. What's going to happen to the two y components? Will they add or subtract? These two green y components, add or subtract them? Why subtract? Yeah, they're going opposite directions, right? And the two black components we're going to subtract because they go opposite directions as well. So we need to do a whole bunch of little micro calculations along the way. Here's how I might do that. The hypotenuse of this purple triangle right here was, I believe, the running back, who is 90 by 7. And this angle right in here is, I believe, 20 degrees. So PY is going to be whatever 90 times by 7 times by the cosine of 20 is. And the reason why I'm timesing by the cosine of 20 is that this right here is adjacent to the 20 degrees right there. Yeah. Did I screw that one up there? No, because the linebacker is red. Yeah, good question though. Yeah, good thing to double check on. Why don't we do the linebacker right now? if I do py for the linebacker is 122 by, what was its speed, 8. And we're going to have to times this. Now to get this side right here, I think it was 10 degrees kind of hidden inside here. See how this side right here is the opposite? So if it's opposite, we're going to have to multiply by the sine of 10 degrees. Now, I'm not actually going to find what those numbers are just yet. I'm just going to write out the basics of how we'll solve it. But this is breaking things up into vectors. Can I say a brief aside here? If you're not sure what the heck I'm doing right now, can we have a conversation, please? Okay, because if I lose you on the vector step here, I need to backtrack. We also need to calculate the x components. So this side right here, so I'm talking about this little guy right here. This is the running back again, right? So it's still 90 by 7. But if this side right here is the 20, the x right now is the opposite, so that would have to be cosine of 20. Oh, there's so much lag on my board right now. And then this one down here, if I'm looking for this side right here, what was the linebacker again? It was 122. Sorry that my 2's suck. 122 by 8 by, this will now be the cosine of 10. What's the whole point of this? These two black numbers right here are the two x components. I'm going to need to subtract them from each other and figure out what the net x is. These two green amounts right here are the y components. I'll have to subtract them from each other to find the net y. What do I do when I'm done? Anyone remember? Once you find the net in x and the net in y, what's the last step? Hypothetically, let's say that you now know your net in x goes this way, your net in y goes this way. Do we want to know just x or y? We need the hypotenuse. How do you find a hypotenuse? Pythagoras' theorem. So give me a sec here. I'm going to try turning off a few things on my computer because this is really laggy. If that's enough for you guys to get started, try solving the rest of the question. Sure. Did I make a mistake on that? For the running back. Oh, I did that twice, didn't I? Thank you. Yep, this one should be sine, shouldn't it? Thanks, guys. I totally messed up there, didn't I? Because it's the opposite right here. I think I said sine and I wrote cos. You're totally right. This should be sine of 20. Okay, you guys give it a try. I'm going to close a few things on my computer because I'm super laggy right now. Hopefully that'll help. I think it's because I have like a million things open right now. So I've got 90 times 7 times cos 20. And we need to have 122 by 8 by sine 10. Okay, so when I subtract those... Okay, so I'm going to start throwing in some values here. In the y direction, I have a very, very large y component going down, a small amount of y component going up. When I subtracted them, my net in y was this. I got 422.5 or so as the net of my y values. And that was me taking this calculation right here, 9 by 7 by cos 20, and subtracting the 122 by 8 by sine 10. The net of that was 422.5. Anybody else get that? Okay, good. Okay. Then when I do the net in the x direction, let me try that real quick. So that's going to be 9d by 7 by sine 20. That's 215. 122 by 8 by cos 10. Hey, is 961. Okay, so 961 minus 215.
12.
Nope.
No,
7.
Tom Brady's number.
Oh yeah, it is. I got 745. I do, yeah.
Okay, because I've got one. I texted Kevin to wear his because we have some triplets tomorrow.
Okay.
So I'm just going to wait on his text. He's got that third one.
Okay. Wear my Brady jersey?
Yeah.
I'll wear my Brady jersey tomorrow. Okay. Did anybody get 745.96 when you took these two black numbers right here and subtracted them? Okay. So then the only step you have left then is once you've taken this number right here and this number right here and subtracted them to go here. Let's color code this better. And if you take this value and subtract them, it goes here. Your last step is to use Pythagoras' theorem for the resultant, because that's what's going to happen is ultimately these two things, when they crash into each other, they're going to go this way when you're done. And we just need to know what that resultant is, which is really what I've drawn right here. So if you take Pythagoras' theorem, that should solve this for you. So 745 squared plus, where's that 422 number? Square that, square root your answer. I got 857 as my resultant. This number here ended up being 857 and change. Anybody else get 857? Or am I on my own on this one? You got 857? You haven't tried it yet? Okay. Okay. Let me know if you didn't follow the calculations here. That would be in a unit of kilogram meters per second. There's one more thing we need to do, though. I didn't actually ask you what the momentum was going to be along this axis right here. It asked you what the velocity of the combined players would be is. So if we've now done all of this vectorness, where there's x and y all broken up into numbers, and you added and subtracted it, and I've now found that there's a component. This is the momentum on the hypotenuse. This is the momentum in x. This is the momentum in y. If this is a momentum number, but we want a velocity, what's the last thing I got to do? Divide by mass. But we have to divide by their combined mass. So if I take my momentum and I divide by the combined mass, what's the combined mass going to be? 212? So if we divide by 212 kilograms, that'll get us our final speed. So divide by 212. With sig digs, let's do sig digs finally. I think I get 2 sig digs. I got 4.0 meters per second. You got that too? Okay. If this is something where, like, as I'm doing work and I've got just numbers all over the place there, if you are lost, can we have a conversation ASAP? And I'll try to help explain better how the concepts work, because it really pulls on vectors. And if you don't understand fully what I'm doing here in terms of vectors, just let me know, okay? It's fine. We need to fix that gap as soon as we can. There's one more thing we could solve for. We could also solve for the angle at which, once this red one and this purple one collide, how they go off on an angle here. We could actually solve for an angle down here as well. Maybe I'll skip that part for right now, but how do you calculate an angle? Tan inverse. All you have to do is know two opposite and adjacent sides right here. And if you just do a tan inverse, it'll give you the angle you require, if such a thing is needed. Okay. So that's the sort of question that if you're not able to do yet, we're working up to that. Okay. There's just numbers that kind of just go everywhere. I know I've just got like random. There's like a 90 by 7 by cos 120 over here, and 90 by 7 by sine 20 over here. You just have all these numbers all over the place. You got to have really good skills at keeping track of what all these different sides are. So, okay, let's move on. We'll come back to that if we need to. Here's the last topic I need to discuss with you. Momentum and energy are so closely related. For anyone who's got one of the formula sheets with them, there are 10 physics principles that are listed down here at the bottom that you're supposed to be aware of. Many of you, I've really explained these last year. There's uniform motion, accelerated motion. two of the conservation laws are conservation of momentum and energy. Okay, they're really almost the same thing. It's just energy's formula is 1/2 mv squared, and momentum's formula is mass times velocity. We have like some definitions I need you to know. The two definitions are elastic collisions and inelastic collisions. What we witnessed yesterday in our lab was an inelastic collision. Did anybody actually have it so the momentum that you started with actually finished what you ended with? No, probably not all that much, right? Why? Well, we lost energy, finger quotes. We lost energy due to friction, sound, heat, that sort of stuff. Was that energy really lost though? No, it just transferred to different forms. So the word we use is that if kinetic energy is conserved, we call it elastic. If all of your motion energy to begins with finishes afterwards and you literally lose no energy to sound or heat or light or whatever that stuff is, somehow if that's possible, that's called an elastic collision. But that means kinetic energy has to be conserved. If not, we call it an inelastic collision. So then it leads to the question, Chris, how in the world are you going to have a collision between things where no energy gets transferred other than kinetic, where literally object 1 hits object 2 and a 100% efficient collision takes place? It's actually going to happen later in this course. But whenever atoms or subatomic particles collide, like say an electron and a proton collide, it is actually possible for no heat loss to take place. Does that make sense? But it would have to happen on a microscopic level, right? On a macroscopic level, as two surfaces rub next to each other, there's got to be loss due to friction, right? But let's say that there's a proton and an electron hitting each other. How is friction going to take place, right? Friction requires a surface for things to hit on, okay? And so that's what we're going to talk about on a future slide, is the idea that these things right here are theoretically possible, but only on the really small scale. Most of the time, we have inelastic collisions, which just means that energy is not really lost, but kinetic energy is. The motion of object A does not completely transfer to object B. Okay? And so you may be asked to not only solve questions that involve momentum, but you may also be asked to solve questions that involve energy. And so I've got one more example to kind of go through. That's the type of, thing you need to be ready for. This is called a ballistic pendulum. Okay? Here's how this works. In theory, what would happen is a gun is going to shoot a bullet. The bullet is then going to lodge itself in the block. And as the bullet lodges itself in the block, there is a collision, not unlike when the linebacker and the running back hit each other. Right? And as a result of that collision, the block is going to swing upwards. Okay? We actually have two things that we can consider then mathematically when doing this equation. At this moment right here, at that very moment right here where these things run into each other, we have a collision. Which means we can try to use momentum conservation, assuming it's an isolated system. Is it actually going to be an isolated system? Probably not. But in an ideal world, all of the momentum of the bullet should hopefully travel into the block as well. Okay. Well, we can also then make a calculation based on the block itself. See how the block is going to swing upwards? It has some kinetic energy right here at this moment while it's in its lower state. And as the block rises upwards, its kinetic energy is decreasing because its potential energy due to gravity is increasing. And we can actually use, after the collision, we can use energy conservation. I'll write that as E conservation down here. And so you may be asked to use multiple sorts of physics principles together. So this is during the collision. And this is going to be after the collision. So one more time. As the bullet strikes the pendulum, there's going to be a huge amount of energy lost, right? I mean, in order for a bullet to burrow inside of a block of wood, isn't it going to heat up? Won't energy be, finger quotes, lost? But ideally, hopefully, momentum is still relatively conserved. Ideally, right? Because even though that heat is lost, was the heat lost to the outside, or is the heat not still inside of the block itself? Does that make sense? Right? So if the heat, if you can imagine that these lines right here are heat escaping, as the bullet burrows its way inside the block, sure, the bullet lost some heat, but didn't the block absorb it? So as a system, isn't this system right here, doesn't it still maintain the same energy it always had? Based on that, ideally, momentum should still be conserved, and we can hopefully calculate how much momentum occurred during this collision. After this collision occurs, the momentum is going to cause this block to then swing upwards, and therefore kinetic energy will then decrease, causing the block to go up, increasing your potential energy. So let's try an example. Probably the best way of doing it. I'm going to take a desk and sit over here if I could, because this is going to require sitting down for some calculations. Okay, say that you've got a small bullet. Like this is, what is that, 14.9 grams? It's fired from a pistol and it strikes a 2-kilogram ballistic pendulum. Upon impact, the pendulum swings forward and rises a certain amount of height above the equilibrium point. So I've got 2 questions for us to try. Number 1, let's find the velocity of the bullet when it was shot. And 2, now that we know some new vocabulary, let's figure out whether it's elastic or inelastic. I already know the answer to this bottom one. It's going to be inelastic. What does inelastic mean again? It means that like somewhere along the way, your kinetic energy didn't transfer perfectly, and some kinetic energy transferred into heat. I know that's going to happen, unless it's like protons colliding. But let's prove it. So, let me begin with a bit of a picture to help illustrate things. Here's a block, and we're going to like suspend it from the roof. And we're going to have a bullet, this is a bullet here, embed itself inside the block. What's going to happen to the block? The block will eventually rise up and swing in an upwards direction. And if energy conservation takes place, here's what should happen. There was kinetic energy for the block, and that kinetic energy should have turned itself into gravitational potential energy for the block as it rose up. How far did it rise? 0.219 meters. So how the heck did this thing go up 0.2 of a meter? Well, it had a whole bunch of speed to it to begin with. So we can kind of build ourselves a formula for kinetic energy turning into potential energy. What's the formula for kinetic energy? 1/2 v squared, yeah. And what's the formula for potential energy, gravitationally? Mass times gravity times height. Okay. This would be one of those times where we have to like build ourselves our own formula. Like there's no formula on the data sheet that I can just point to and say, oh, this is the one you use. You have to understand physics principles and get that this height right here came as a result of the velocity. If I go back a slide right here, why did this block go up that high? Well, because it had some incoming speed. Right? And in theory, all of that speed should carry this thing upwards until it finally comes back down again. Hopefully that makes sense. Okay. Now, what's really cool about this example right here is that mathematically, even though we're building our own formula, I can actually remove one of the variables. What variable is not relevant? Yeah, mass. It's on both sides. I can cancel that. Let's start filling in some of the information I know. I don't know that I know any velocities, do I? Because like if I read through the stem, is there a velocity given anywhere? No. But do I know G for gravity? Yeah, 9.81. Do we know the height of the block raised up? 219. So why don't we solve for the velocity of the block? What I'm saying is that after this thing collided, what we're really solving for is this velocity right after impact. That's what we're now solving for. So I'm just going to mathematically rearrange for V. V would be equal to 2 times G times delta H, all square rooted. So I'm going to take the 2, bring it over here. I'm going to square root both sides. But I want to be really specific. This is the velocity, not of the bullet, but of the block after impact. After impact. Was the block moving before impact? No. So this is the second after the bullet lodges itself inside. Okay, so let's find that now. 2 times 9.81 times, what was the height? 2.1, 0.219? Where's my calculator? Okay, and when you square root the whole thing, I got 2.07. I like to put dots afterwards just to remind me that that's an unrounded number. So I want to save that number for future calculations. But that's the speed of the block right after impact. If I go back up in my picture right here, this bullet had a velocity originally. Its velocity initial is what we don't know. This block right here, it has a final velocity now of 2.07. It's kind of a mess now, but it has a final velocity of 2.07 meters per second. Because what was the block's initial velocity? Nothing. Right? Wasn't the block at rest originally? So the block went from 0 up to 207. The bullet must have gone from really fast down to 207. Say that one more time. The block itself went from nothing up to 2.07 meters per second. The bullet went from a couple hundred meters per second. Why didn't it go down to 0, by the way? Because it's still in the block and the block is moving. Well done. Yeah. Right. Let's even try to write that out. Bullet is going to go from something down to 207, while the block is going to go from 0 up to 207. That's kind of our logic. So we now have a little more work to do, though. We now can consider the collision part of this. So now consider the collision part. Kind of like do a bit of a page break and consider the collision. Before we began, there was the block. It had a mass and a velocity. And before we began, there was a bullet. It had a mass and a velocity. After the collision, the bullet is lodged inside the block, right? Well, I think what we need to do is we need to add their masses together because they're now combined, and collectively they have a velocity. That's kind of how I'm going to build my equation. This thing had some momentum, this thing had some momentum, and then afterwards they collectively have some momentum. That's going to be my formula to kind of start building this. Although, what was the mass and velocity? What was the momentum of the block, though? 0, wasn't it? Because it wasn't moving. So I can actually eliminate this entirely because the block itself isn't even moving. I can build myself this formula here. The mass and the velocity of the bullet, because the bullet is the only thing that provides propulsion, should equal, when we were done, the collective mass times the velocity of them together. This is the formula we're going to use. And this is what makes physics so darn hard, is that sometimes you get to use a formula right off your data sheet, and sometimes you have to have such a good understanding of what's happening because you have to build your own formula. We've now built ourselves a formula. But the formula always changes depending on context. You get what I'm saying? Because these two things embedded in each other, you have to add their masses together. What was the whole point of our question again? Wasn't it to try to find the velocity of the bullet originally? So if we want to find the velocity of the bullet originally, divide both sides by mass, and I think we're good to go. We're now ready to start plugging numbers into a formula. The velocity of our bullet will be equal to the combined masses. So let's combine the masses of everything. It'll be 2.0149. That's the combined masses. It'll be 2.0149 kilograms. That's the combined mass. How fast were they traveling together? I think it was 207, wasn't it? Didn't we calculate that a little bit earlier as our halfway point? So I'm going to write 2.07 ... Don't forget, don't use the rounded number. Use the actual full digit in your calculator. And then the final step is we then have to divide by the mass of the bullet itself, which is 0.0149. This top mass is the mass of them collectively. This bottom mass is the mass of just the bullet. And that should give us a formula that tells us how fast the bullet was going originally. 2.0149 times by the 207 number, divided by 0.0149. If you do it correctly, as long as I did it correctly, I got 280 meters per second. got that too? Is that a reasonable speed for a bullet? Yeah, that's in the ballpark for sure. Let's just do a quick recap then of all the calculations we did. And like I said, what makes this frustrating is that there's no like one formula that you kind of use. You have to like build it yourself. You have to understand physics principles so much in this section here. You have to understand that the block itself was stationary beforehand, and then it rose up. The reason why it rose up is that as soon as the bullet lodged itself inside the block, there was now kinetic energy in the block. The kinetic energy in the block causing it to rise up means the kinetic energy turned into gravitational energy. So we made 1/2 mv squared equal mgh. The mass was actually technically irrelevant because it canceled. We did a math equation and we found the velocity of the block immediately after the bullet lodged itself inside. So the block went from 0 to 207. The bullet apparently went from 280 down to 207. That's what we did in the second half of the calculation. We said once we kind of got a visual picture of it, the block itself wasn't even moving. I put a big fat 0 through it. But the bullet was moving. We just didn't know how fast the bullet was traveling. So I said mv for the block and mv for the bullet, whatever momentum you began with, should equal to the momentum of them when they were lodged together. And when they're lodged together, I added their masses to each other. Well, once I canceled off this mv right here, because the block wasn't moving, I made an initial formula of this. Why did the collective mass move with a velocity of 207? Well, it's because the bullet was moving with a pretty high speed. So then to find that speed, we divided both sides by m. And if you can kind of follow along here then, this is right here, the mass of the bullet and block, which is the 20149. The velocity of them together came from my halfway point, and this mass right here is the mass of just the bullet, because the bullet's what provided the initial impulse. And now we got our speed. Whew. It's hard, hey? It's a lot, because you not only have to have wicked good math chops, you have to have good conceptual skills. Okay, let me do one more thing, and we're almost done our lesson, by the way, because I'm only going to do just the one example. I can make more if you'd like later. That was only half the question, though. We did find the velocity of the bullet as it was shot. We also have to just confirm whether the collision was elastic or inelastic. I already said I'm fairly confident we're going to lose some energy due to heat, right? Like, a bullet is not going to lodge itself in a block without there being some loss of energy, but we should prove that. So if I can kind of do one more page, let's prove that. Again, a picture. Before we had the collision, we had a bullet, and we had a block. Well, what was the kinetic energy of the block as it was standing still? 0. Okay, so don't need to worry about that. What was the kinetic energy of the bullet as it was moving? Well, now I can do that. Its kinetic energy would have been its mass, which was 0.0149, by its velocity, which we just found, right? Wasn't the velocity 280? Squared. So I should be able to find the kinetic energy of the bullet initially. I'll just put I, if that works. So take this number and square it, times by its mass, and divide by 2. The initial amount of kinetic energy that the bullet brought with it, I have as 585 joules. Do we expect all of that energy to have got transferred into the block? Well, actually, yes. But did it all remain as kinetic energy? No. I still think this is a more or less closed system, maybe even isolated-ish, because did the heat of the bullet embedding itself in the block, did the heat leave the system entirely? Well, no, it just meant the block got hotter, right? So the heat's still inside there, but it's not in the form of kinetic energy. Because now that we're done, now the after amount is you've got your block, you've got your bullet inside, and now it's got kinetic energy. It's 1/2 of mass, but now we need the mass of everything, right? Because the bullet is inside of the block. So the mass will now be 2.0149. And then wasn't the velocity of the block after it began to move, wasn't its initial velocity like 2.07 or something? squared. So if I try that, I just got to go find those numbers in my calculator. 2.07 gets squared. I multiply by 2.0149 and divide by 2. The amount of energy kinetically that was left after the collision, I only ended up getting 4.33 joules of kinetic energy. Final. So is this an elastic collision? Not even close. Like, as a percentage, that's like, what, less than, let's see, 50 would be 10%, 5 would be 1%. This was a less than 1% effective collision, right? 99% of the energy was, finger quotes, lost due to heat. Does that make sense? Okay, let's do a summary and then we'll call her quits for the day. So here's my last slide. When we're doing microscopic collisions, which we will eventually get to, by the way, when we finally start talking about atomic physics, we'll discuss what happens when electrons and protons collide. It is actually possible for there to be no heat loss, right? I mean, what causes friction? Two surfaces rubbing together. You'd actually have to have a surface. If we talk about particle accelerators, which we will eventually, and you have a proton and an electron smash into each other, there's no surface for friction to take hold of, right? So it is actually possible for there to be no loss of heat whatsoever. That is possible. If that occurs, we call it an elastic collision. Most of the time, though, that's on the microscopic level. On the macroscopic level, which is like the everyday life example, it's usually inelastic because you're going to lose that energy. Usually heat. You could also lose energy due to sound, right? Like when you had the two pool balls hit each other, it made a click. It's not a lot of energy, but that came from somewhere, right? You could also cause objects to change their shape due to warping and bending. And although that's not a form of energy, that's a form of work. Like, let's say that you have two objects smash into each other, and one of them bends a little bit. Work was now done to deform it. But if you guys know, work is the same as energy. So those are usually the examples of what happens in a collision. Okay. Even this Newton's cradle will slow down. You guys have seen this Newton's cradle before, right? We've talked about it, right? Is it losing energy? Slowly but surely. Really, every time this ball clicks into that one, that one, that one, and that one, a little bit of energy is lost to sound, a little bit to friction. Up here where the pivot happens to exist, there's probably a little bit of friction up there. This is one of the most efficient machines that man has ever made, though. Like, it's probably 99.9% efficient, but it will eventually slow down due to that loss of energy over time. Okay, questions? Anyone have any questions? Okay, let's talk big principles you need to know then, and then we'll do a summary, and you guys can do what you like for the last few minutes of class here. In the unit of momentum, you need to know what vectors are. You need to know how they work. The very first question that I started class with, please, please, please let me know if anything I did here was not something familiar to you. I know sometimes when I write on the board here, it gets a little messy over time. But if conceptually you don't get the idea of how to calculate this side, that side, and that side, if that's a bit of a struggle, we need to have a conversation. I need to help you with that vectors concept, because that's like 2/3 of what we do math-wise in this unit. Okay. You got to be able to separate into x and y using cosine and sine, add and subtract from each other, and put it all together when you're done. Okay. Another thing you need to know is all the theory behind it. You need to know momentum by velocity mass by velocity is momentum. You have to know what makes momentum different from impulse and how they're both really the same thing as inertia. You got to know Newton's laws. Okay. When we eventually write tests and stuff like that, less than 40% involves math calculations, which is kind of good because maybe you hate doing the math. But like most of this course is theory and interpretation, just so you guys are aware. You need to know the new terms of elastic versus inelastic. It's nearly the same concept as isolated and closed and open systems. Like, it's really along the same lines, except an elastic collision is when kinetic energy is conserved, not just all energy. Energy is always conserved. Energy is never really lost. But if you can conserve your kinetic energy, we call it elastic. Okay. Most things don't have that happen unless you're like an electron. On the board over there, I have a picture still of some graphs and the equation F delta T equals M delta V. You should know how those graphs and those relationships work, where there's a direct relationship versus an inverse relationship. Okay. So, and that's it. That's kind of more or less our unit. Okay. So like I started class with, here's where we're going to go from there. Tomorrow I've got a day set aside for you to work on stuff. Okay. It's just a flex day. You can work on whatever you'd like to tomorrow. Hey, Bill. Yeah, vectors. So tomorrow, here's a couple things you can do. One, if you'd like to, you can keep working on that lab. Okay. Look for the feedback I gave you on Moodle and see whether or not I have any suggestions for improvement. Two, we did a group assignment in class a while back. If you haven't practiced those questions, that's something else you could do. Okay. A third thing you could do is, now that I've shown you where that practice quiz is online, you could start trying some of those questions if you want. Okay. Next week, we're going to do two main things. We're going to do a new lab, and we're going to do that group test. Right? And we'll just do some practice questions and see whether we can solidify our knowledge.
Can we do the topology group test too?
Bill, can we? I was all for it. All right. Were you looking for me, one of these guys, the whole class?
Someone might have the wrong class.
Who? Langerman is, but he's not here today.
Oh, he's golfing.
Golfing?
Important things he's talking about, like volleyball practice, not golfing.
Where it is?
Don't even get us started.
Okay, guys, you can feel free to work on whatever you want for the last 15 minutes, okay? Call me over for help as you need, okay? But I'm kind of done for the day, so. Let me just stop the recording.